All right, so basics of graphing. In math class, you've got the quadrants, right? Where you had quadrant, what was it, 1, 2, 3, 4, right? And so in econ class, we generally are in quadrant 2 because we're talking about positive things. And so when we do these quick graphs, which we'll do 100 of them, at least, I don't think I've ever counted them all out, but we will fairly regularly, you know, I'm going to drop this thing back. We'll just do, okay, price, quantity, and the demand curve, or something like that, right? And so we've got these positive numbers running on both sides. And the thing that's drawn in the middle, I actually like to think of as a collection of points rather than a line. And the reason I like to think that way is that it reminds you that out in this space there's 2 dimensions to it. And so this point has this price of $5, people are buying 100 units, right? So it kind of reinforces that, that notion. All right, so let's, let me get this scaled down. That's really down. Okay, so we'll often look at data with points. So the point in the space has the 2 dimensions. And that can set up a graph, or the next slide is the scatter plot on page 15. So here, remember when I talked about schedule goggles? So here I've got movies, tickets, DVDs. So we can look at, sometimes there'll be a problem that'll just have the schedule of numbers, and then we can take that data and plot it into this space, right? And what relationship comes out of this? So we've got DVDs getting more sold as we go up, and we got box office tickets sold. So is the number of tickets sold at the movie theater a good predictor of how many DVDs will be sold? In other words, if we sell a lot at the theater, high ticket sales at the theater are correlated with high DVD sales. So do you start to see that trend? Like if I was to kind of approximately average out these, that we get something that maybe fits in there like this?
Yeah.
Okay. So that's showing a positive relationship between box office tickets sold and DVDs sold. In general, we might start to be able to make a claim that more box office tickets sold leads to higher DVD sales. And that's a positive relationship between those two variables. So don't be scared by the word variable either. Whatever we're measuring on the horizontal and vertical axis ends up being our variables. Okay. They mention a scatter plot down at the bottom of 15. And sometimes we can track stuff over time. So notice what's going on here is we've got income and what is this, expenditure in 2001, 2002, 2003, 2004, right? So just different ways to kind of show relationships between variables in this 2-dimensional space. All right. Let's see if this thing works. Oops, that one. PowerPoint. Yeah. All right. Next page, page 17. Here's these relationships. We'll see a lot of this in different things we look at. All of these relationships, which the fancy word we put on is a function, all of these three functions are showing that positive trend. But they're shaped differently, right? So this is a linear relationship, which means kind of like what we did with the production possibilities frontier the other day. If I increase 20, I get 200. Increase 20, I get 200. So the rate of change, or the slope of a line, is constant along the whole thing. So that's giving us just a straight line positive relationship. Whereas here, see the curve is going up? And so it's actually accelerating. So as we move this direction, things are going at a higher and higher rate, which is connected to the slope. Now, do you guys remember the slope of a curve? Remember the tangent line? Does that ring a bell? To find the slope of a curve, you find the tangent line, the slope of the tangent line to that curve. Tangent, yeah. So tangent is the word. So it's just, so you find a point where it's just kissing. Now, if I find the tangent line to a straight line, it lies right on top of it, right? So when I come over here to the curve, I can find the slope of the curve at a point by bringing a straight line up to it called the tangent line until it's just kissing that curve. And then it's going to kiss it at one and only one point. And then the slope of this line at that point is the slope of the curve at that point. And if we look and do the same kissing exercise up here, that slope is steeper up here. So with this relationship, we've got a positive relationship, but it's increasing at an increasing rate. The one we see in econ a lot is this one, where things are increasing at a decreasing rate. So as I increase study time, how does that shape up with my, what is that, problems worked? Okay, I was going to even think we could even look at probably grade performance on how well you did on the test, right? Study, study, study. The first bit of studying gets you from a F to a C pretty fast. But then the more you study doesn't necessarily improve your grade. And eventually you get to a 92%, but then to study even more only gets you maybe a 94%, 2% better, right? And so the results are increasing at a decreasing rate. The law of diminishing returns is the one we use in school, or in econ. All right, so those are different types of relationships for variables that are positively related. Okay, questions on that one at all? All right, page 18. Here's our production possibilities frontier. So vote outward. This is a negative relationship. Leisure goes up, problems work goes down, right? So they move in opposite directions. It's a negative relationship between those two variables. And this one is the slope again. If we're thinking about the tangent line, the slope is pretty flat. If we do the rise over the run, which they go over the rise over the run a little deeper in this, so I'm kind of jumping a little bit. Rise over run, or it's actually fall over run, is pretty flat. Down here, when we have a whole bunch of leisure and a little bit of time, or problems worked, the slope is very steep. The rise over the run is a different number. So that's the one connection that we were talking about yesterday with the production possibilities frontier, is that the slope or the cost ends up changing depending on where you're at. We got the linear relationship, the slope is constant across it, and then we could have this negative relationship where it's declining, but it's becoming less steep as we go. Okay? Make sense?
Mm-hmm.
Right. There we go. Page 19. So here we've got rainfall and wheat yields. So we're looking at the crop. If we have too much rain, we drowned out our crop, right? If we don't have enough rain, we have a drought and our crop doesn't grow. So we've got this idea of a maximum yield. At some point, there's an ideal amount of rain. So the optimal amount of rain happens there, and that's at that peak. Okay, and then the minimum points. Now, if you put these two pieces together, check it out from what we just did. If I just take this half, we have a negative relationship where the slope is getting flatter. And then if we think about that half, it's getting bigger. Okay? So minimum and maximum points. Stop, jump in anytime, any little question, even something that you think is dumb, it is not dumb at this point. So bring it on. Once in a while we see relationships like this, which actually means no relationship. So when we have a horizontal line or a vertical line that's perfectly vertical, there is no connection between the two. If I have more French wine, I don't get more rainfall in California. So they took two things that were obnoxiously apart from each other, right? So otherwise, if it was a positive relationship, oh, the more wine they make, the more rainfall we get in California. Or a negative relationship, the more rainfall, or the more French wine, the less rainfall in California. Neither of those things are true. Those two things are independent of each other. And so when you see a line like that, that means there is no connection, no relationship between the two.
So if like that were to be a text question, just randomly, like where would you put the line? Like would you just pick 1, 2, 3, 4?
Yeah, actually, if a question was related like this, it would say, currently the output of wine is $3 billion, or 3 billion gallons. And so then you'd know that 3, it would go right at the 3.
Okay, that makes sense.
If I was doing it generically, we might just say, suppose, because I will do this in class. In fact, I'll just give you a class 1, would be the long run aggregate supply curve. I'll just put quantity and price since we haven't talked about any of this yet. And this is at this level, Q1 of output. See how I left it all generic? Like, so what you guys need to know is that that generic thing is just a number. I could have went 1, 2, 3, 4, 5, 6, 7, 8, 9, but I didn't. I'm just using a generic number here to say, and this is the relationship. It's no relationship, that it's vertical. Okay? Good. Anything else there? Okay, page 20. This is where I've jumped the gun. So here's the slope. Now this way of writing it, change in y over change in x, comes to us from the slope-intercept form of a line, which I think we talked a little bit about in class. So y equals mx plus b is one way that we write it. You remember that? Sometimes people put an a here or whatever. So that's the slope, that's the intercept. And that describes a straight line. So how that would look like, what that would look like if it was a positive line, I guess I'll keep this in yo-yos and x-rays here. So y equals 2x plus 3. So the intercept is 1, 2, 3 graphically. And then the slope is this number. And that is the change in x over the change in y, which is what they're tying it to here. I prefer rise over run. The rise is the vertical axis, the change in y is the vertical axis variable, and the change in x is whatever you're measuring on the horizontal axis. So if you kind of remember rise over run, it doesn't matter if this is a q or this is a p or if this is cars and this is food, right? Like we were doing in class the other day. So the other little trick that's helpful here is to, if you've got a number, is to put it over 1. Any number can be put over 1, right? And so now you've got your 2 over 1, rise over run. If we put it back in that context, change in y over change in x, that's the slope of this line. So at 3, I'd go up 1, 2, up to 5, and over 1. And that represents another point on this. So the run is 1 unit, and the rise is 2 units. Okay, questions on that? A little bit of review, is it starting to come back?
Yeah.
Okay. All right, so the picture here just shows a couple examples of the slope of a straight line. 4 over 3, 3 over 4. Remember, when it's a negative relationship, then you can think of a fall, a negative rise. So down 3 over 4, if the slope is a negative 3/4 in that case.
Now, the thing that I kind of got confused with is in class, whenever we were doing the rise over run, and you were like, actually, it would be -2 or -5 on the Japan.
Yes.
Do I need to know why that's?
Yeah, I mean,
'Cause
as
I
far
was
as this
like, what?
context. So here, the slope is positive. If I connect these two lines, it looks like that, right? And so the slope of this function is positive. And so the slope is positive. What we were doing in class was more like this. And I said, what's the slope of the line? Let me use what was in class. What was it? 25 and 5, right?
Yeah.
This doesn't look too pretty, but so the rise over the run, since it's negative, the slope of this line is a -5, which is down 25 is how I would think about it, and over 5.
Okay. that
See
makes
what I
sense.
mean?
Yep.
Okay.
Okay.
And then that gives you your -5.
There, okay. Yep.
And the connection that's specific to economics is that the cost, the opportunity cost of another unit of food was 5 cars. So that's kind of expressed as a positive because it's a cost. See what I mean? Like when we go to the store and say, well, how much did that Starbucks cost you?
Yeah.
Well, it was $2.39. How much did a unit of food cost me in Japan? It cost me 5 cars. But the slope is -5.
Okay.
All right. '21. This is what we just did with the tangent line earlier. So here's the curve. And at point A is a tangent line to the curve at that point. And that is the slope of the curve at that point. And so what you're calculating is the slope of the straight line. And so the way they've got the numbers here, we're going rise over run 3, and we're running 4. So 3/4 is the slope. All right, good on that one? Okay. This one I don't even think is worth quite going over. This is something pertains more to micro. So I think I'll skip that one.
You're taking micro? You're taking next semester?
Yeah.
Nice.
Yeah.
Me too.
Yeah, so you'll have that. We can worry more about that. If you get through this, you'll get through that fine. Okay, now this is super important. Shifts. So, when we draw a relationship between two things, we got ice cream consumption and price. So this is the price of an ice cream cone. As $2.25, people are going to buy 20 ice cream cones. That's when the temperature is 70 degrees. So we're holding constant things besides price and quantity of ice cream. As temperatures rise, people want to buy more, and we can think about that a couple different ways. One way is that they'd be willing to pay more for ice cream. Charge $2.25, charge $2.75, I don't care. I'm going to come to there. It's 101 degrees out. The higher the temperature, the more is the willingness to pay. And so this kind of captures that by people's willingness to buy ice cream when temperatures are 90 degrees. And so it relocates the curve to the right. So this is really a demand curve for ice cream. So we got price, and we've got gallons consumed with 70 degrees, gallons consumed with 90 degrees. So let me connect that back to you for the production possibilities frontier we were doing the other day. Shows the maximum combination of two goods an economy can produce given its available resources and technology. So Japan had 1,000 people. What if we doubled their population? Would they be able to make more? Yes, right? So maybe if we doubled the way, even just, I guess, simply using the numbers we had, it might be reasonable to say we were making 5,000 food with 1,000 people. Now we can make 10. And we were making 25 of 1,000 people. Now we can make 50. And so that whole curve would shift outward with more resources. Okay? So it's really, it's a way to, the way they've got this worded is good. It's kind of a way to graph three variables. Because we were just measuring, without the red one here, two variables, ice cream and the price, quantity of ice cream and the price. And by having two of these up here, we're really graphing a third variable, 90 degrees, right? And 70 degrees, the relationship between. Okay. I think we're about done. This is the.
This is chapter 1.
This is so page 24. Yeah, this is chapter 1 appendix. So page 24, we did what I just did earlier. So y equals a plus bx is the slope-intercept form of a line. The intercept is the a. The slope is the b part. So whenever you see something that way, that's what we're dealing with. I think they're just bringing in shifts here. So if you look at these three lines, y equals 100 plus a half x, so the intercept was 100. So that shift is actually the intercept term. So here, y equals a half x. All we've done is eliminated the intercept. It's really 0, and it's right there. And then if we have it at negative 100, it would shift down. So that's kind of another way of visualizing a shift of a curve through the equation, having our equation goggles on. All right, that's it. Do you feel like you got any other unmet questions?
Mine would be on Blackboard, just to make sure that I have it right. Everything, like the homework, and I think there's a math quiz right for this week.
Yes.
And then the test, it's all due at midnight on Sunday.
Right.
But